We're going to start doing some actual stats. So you've been learning some tools for um, managing data in R, and through that, learning some basic programming concepts. Um, we're going to start both learning sort of concepts in the realm of thinking about generative models for data, that is, thinking about how data came about and formalizing those ideas into algorithms that produce data. This is one of the reasons why at the outset I'd suggested that this course could alternatively be thought of as a course in how to commit data fraud, because we're going to be learning how to generate fake data. Um, and when once we sort of have, or simultaneous to ideas about or exploring different models and ways of generating fake data, we'll be dealing with or learning some tools to do inference on those models given a data set that comes to us in the real world. So that latter is going to, we're going to start using, not Chrome, not desktop. We're going to start using a piece of software called Stan. So let me close this. I'll open up Chrome, open up a new window. So the assignment for this week, part of it was just get Stan installed. Stan's main website is mc-stan.org. Stan isn't an acronym, it's just a name. It actually is named for a fairly famous statistician in the Bayesian world. And Stan is a whole separate piece of software. If you use R, you can, well, it's a whole separate piece of software, but they provide a number of different interfaces for Stan. So the main one that we'll be using is RStan. In fact, the only one we'll be using is RStan. But if you're a Python developer, you can use PyStan. If you want to just use the command line, you can use some command stan. There's one for MATLAB, Julia, and Stata as well. And what all these interfaces do is, say we're in R, it allows us to write code in R that sends packages of data to Stan. Stan will do its thing and send us back its results. So that's what the RStan interface does. When you install RStan, which is described in the quick start guide that I had sent you, when you install RStan, it automatically will install Stan as well, sort of behind the scenes in your R package directories. So even though I've said that there's this separate piece of software called Stan, and RStan is the interface between R and Stan, simply installing RStan by going through these getting started pages will install Stan in the background. So you only need to worry about following these instructions for installing RStan. As you may have seen when you go through, there's some steps to install things. Probably talk to me outside of class if you end up encountering any issues with that. I'm more familiar with the Mac and Linux installation, less so on the Windows, but I'll try to help as I can. So RStan, I'm just going to go back, or sorry, Stan in general, I'll go back, has, again, this nice website. There's a documentation page that you can get the language manual. You can look at that. We're going to be building up, that sort of kind of assumes that you're relatively familiar with the idea of Bayesian modeling and some of the general models that one would want to talk about. So it's probably a little beyond what, it's probably a little advanced for you right now. So I'll be stepping through it. But this will be a good reference manual down the line if you have sort of a specific model or technique in mind and you want to look up like how to do it. So how do I do A time series model where you have autocorrelation in the model. How do you do a multivariate model? Things like that. All right, so there's another site that I guess if you already had Stan installed and you wanted to follow along with some of the examples that I'm going to do this week and next, there's a website called GitHub that lots of people put just code that they're working on up on GitHub. I have a page, Mike-Lawrence, Lawrence. And if you put another slash and put Bayes, Bayes _days, that'll bring you to a page that looks like this. And the critical thing here is the big green button that says clone or download. And having clicked it, you can click download zip. That will download a little zip archive that is really small. So I will open that up and that will open up right there. So I actually already have it downloaded and opened. So here's the folder. I'm going to go in that folder. I don't have RStudio open at all. So that means that if I go in this first folder, 01, one group, and I see a couple files in here, there's a .r file and a .stan file. I haven't told you about what we're going to be doing, but if I double click this .r file, that's going to open up RStudio. It's going to set the working directory to the location of that .r file, and it's going to open up that .r file. So we can see that the working directory is set to that same place, looking at the files. All right, so this is our code that will use the rstan library. It's also going to use the ggmcmc library, so if you don't already have that installed, you'll want to install that. And this is going to work through a particular example of data analysis. So before we actually look through the code, what I want to do is show you, give you some drawings to illustrate what I'm talking about. So I will use my handy scenario here. All right, so I'm drawing upside down, I guess. So let's imagine we have sort of an imaginary line of measurement. Let's maybe say we're doing I, and oh no, I have to do it over here. IQ. Okay. And actually, I'm going to turn the autofocus off. So give me a second. No. Where do you go? Oh, I minimized that control panel. So webcam, focus off, and focus the page. Okay. Oh, this is going to be terrible. Okay, so let's say we have a line that's representing various IQ scores. If I had sort of generally IQs tend to fall at the, I guess, 100, and rarely do you see IQs less than about, say, 60. Oh, that's upside down, I guess. Oh, I have to do it not. Yeah, but I can't do it backwards. So 60. Yes. All right. I'm definitely gonna have the camera properly switched next time, so that it won't be as painful. And you generally don't really see values above 140. No, I have to do it upside down, but not backwards. Okay, so. And do the 4 as this. You can see what I mean. Okay. Okay, so if I went out and I sample the person, I might see that they got a score of about, say, I don't know, call that like 102 or something. Sample another person, got that score, sample another person, that score, and I keep sampling, and we're getting scores that are generally going to be clustered sort of around, maybe they get an extreme one here. They're going to start clustering around here. Now I can start doing some histograms and things to bin this. If I were to sort of do this infinitely, you kind of expect that the sort of distribution of things, as I got infinite observations and did a histogram and started having sort of infinitely narrow bars, that you're going to start getting a generally sort of curved shape like that, such that the sort of center of the highest part of this curve is somewhere around the mean we expect of 100, and it's got some sort of spread that defines how variable the population is, one person's score to another. So that's if we sort of sampled infinitely. If I instead just had, again, let's put 100 here because that's easy to write, and it's going to be IQ. If I just had a few samples, it's hard to sort of write them there, but you get the sense that I get a few samples that are like this. I'm going to ask a very specific question about this. This is a somewhat artificial scenario. I'm going to say, I know that I'm going to try to generate I'm going to express a model where I say, okay, in general, the shape of the population from which these samples were drawn probably has that same bell shape as I drew before. And I'm going to say that I don't really care about the width, or at least I'm going to assume the width of this bell is precisely some number, let's call it. So with IQ, the standard, the sort of expected standard deviation is 15. So I'm going to go ahead and just assume that 15, oh, yes, yeah. I'm going to go ahead and assume that 15 actually does describe this scenario. But I am going to accept that maybe I'm uncertain as to whether this sample was drawn from a population with a mean of 100 or a population of a mean that was somewhat different from 100. So again, there's sort of an expectation with IQ that a random sample will be about 100 and have a variability of about 15. I'm going to assume that the sample that I've drawn still has that variability of 15, or is drawn from a population whose variability is 15, but maybe this is a particularly smart population that I've sampled from. So the sample, certainly, if you computed what the precise mean is, it looks like it's going to be sort of somewhere around here, so a little bit above 100. But I'm uncertain as to where the population value, the population sort of that I sampled. Say I went to, I don't know, PEI, and I measured a bunch of people, and the question is the population of PEI sort of any different from the regular population that the IQ was sort of standardized on? So I've got this sample of PEI people. I want to make inference about the population of PEI people. So I can't just use the empirical mean here from this sample to talk about the population. I need to take the data and integrate it with my prior beliefs about what the population is like. So here, again, we're going to express a model where we use the normal curve. The normal curve has two parameters associated with it. One is the variability, and I've already said that I'm going to just assume that PEI folks have a variability from one person to another of about 15. So that sets the variance parameter for the bell curve. But I am interested in doing inference on where this curve should be located. Should it sort of have its peak right here on the number line, or should I sort of shift this curve right over and have its peak right here, or should I shift it over and have its peak right here? So that's the inference question. It's usually you're not certain about what the variance is, but I want to sort of construct a somewhat artificial scenario where we are only uncertain about the shift, not about the variability. And that will work up to scenarios where we also are uncertain about the variability. So if you want to connect this to your prior education in the context of frequentist statistics, we're talking about the z-test here. Typically, the z-test is what you use when you know what the population variability is, but you want to know where the population location is. And you're assuming a Gaussian distribution for the population. So we're going to do something, the Bayesian equivalent to the z-test. So whenever you have a scenario where you're doing Bayesian modeling, as we expressed the other day, you have your data, you have your sort of generative model for how the data should come about. And that generative model in this case is a normal distribution with a variability of 15, but an unknown shift in where the mean of the population should be. So let's call that shift parameter mu. So let's see. I'm just going to write things, and it's going to be a little bit upside down for you guys. So let's down here. Nah, that's incredibly hard to read because I have incredibly poor penmanship. Anyway, the little arrow indicating sort of how far to shift this distribution. Imagine it sort of shifting back and forth, and every sort of amount of shift is a possible sort of candidate for what the population is. Let's call that amount of shift mu. Now, so we have a scenario where you say, I guess it's y is distributed as, okay, how do I write an upside down n? It goes from top. Wait, now I forget what an n even looks like. Yep, n. So that's sort of, so n and then parentheses is meant to convey that something's normal. And comma. So a normal distribution has two parameters. We'll call this one, upside down. Yes, that's actually a good idea. Let's call this, I don't know, x. X is upside down or not, that's fine. And then this is that 1 and then upside down 5. Yes! All right. Okay, so that's our generative model for the data. So it's going to be a normal distribution. These x's come from a normal distribution with some unknown mean x, but unknown variability 15. So we've expressed our generative model. We've got some data. Does anybody remember what else we need to start doing Bayesian data analysis? So you're thinking about the actual Bayes ratio calculator. So you're talking about the thing at the denominator of that equation. You actually don't need that. That establishes a scaling that's, if you have the same data, it integrates out. You don't need it. But what do we need? Oh, sorry. You know what? I think, so yes. And actually, when you said prevalence, I was thinking about probability of the data, but you're talking about the thing that we do need, which is the base rate. So using terminology that we had from the other day when you were talking about the rates of cancer and probabilities of cancer, it was that base rate that you needed to combine things. Here, the thing that's on the x-axis isn't a probability, it's a just a continuous thing. So a more generic term for that is the prior, what your prior belief on the things that are unknown in this thing. So the thing that's unknown is this thing called x. So you need to decide, again, imagine sort of a line for IQ, and here's, say, 100. You need to decide before seeing any of this data, what you sort of believe for the population that is going to be sampled. So imagine you didn't sample this, you didn't look at the population yet, and so you don't have any data, and you are sort of guessing ahead of time what the likely population mean is going to be. Another way of expressing that is to ask yourself, how surprised would I, to go along this line and say, how surprised would I be if the mean was there? So let's actually draw that over on this side, and I'll say upside down. Oh, well, I'll just call this S. Oh, shoot. Yes, backward. S. Yay, S. S for surprise. Okay, so without seeing any data from a population, you probably wouldn't be very surprised if it was down at 100. Let's say this is 140 and this is 60. You'd probably be pretty surprised if, like, the population had a sample of if the population's true mean intelligence score was 140. So that would be pretty surprising. Similarly, you'd be pretty surprised if the population had a true intelligence score mean of 60. Maybe you wouldn't be super surprised if it was 102, similar to 98. Maybe you wouldn't be surprised if it's, say, 110, or you'd be moderately surprised if it was like 110, moderately surprised if it was 90. So you can start actually drawing out like a curve. Now, you could actually just have like a triangle that defines that curve. So let's actually stick with a triangle for now. Whatever curve sort of expresses your surprise, you can just invert it to express the probability. So if you were to take this same curve and instead of S there, we have a P. Oh, no. Just do a backwards, an upside down P. So this and yes. Yes. That's a P, right? Yeah. I've even got it flipped in my head seeing so many backwards things up there. Okay, so surprise down here, probability up here. So if I'm not very surprised by something, that corresponds to me thinking that it has a high probability. If I'm very surprised by something, that corresponds to me saying that it has a low probability. So ditto for all these other points. So I could sort of express a general sort of function form of my surprise, having this triangle. It turns out that mathematically that isn't very useful, or it's much more conventional to not use like these straight lines expressing your surprise. It might actually be nicer to express your surprise such that it sort of tails off gradually and doesn't actually sort of immediate, because these triangles, they'd actually eventually hit the axis and express that beyond some point you have zero, zero surprise, infinite surprise, yes, and you're expressing zero probability. So better would be to have some smooth function that sort of expresses your belief, and a really convenient smooth function that's typically used is the normal distribution. this is going to become very confusing because we're using the normal distribution to express how the data came about. We're also going to use normal distributions to talk about the shape of our beliefs. It's merely a convenience that we're using the two. In fact, when we start talking about models with uncertainty on the variability, we're going to have belief distributions that aren't normal. We might use a log normal or a Weibull distribution or something like that, maybe even an exponential distribution. But for this particular circumstance, it's critical to sort of keep separate in your mind the idea that we're using a normal distribution to express how the data were generated. But for the thing in the data generation process that we're uncertain about, we're going to express a normal distribution on relating how credible we find each value. So, well, you can just draw sort of what might be sort of a normal looking curve through there. So that doesn't look normal at all, it looks very skewed. Let's imagine that I drew that actually symmetrically. So having chosen the normal distribution as the shape of our belief distribution, our belief on sort of how, or the inverse of how surprised we would be for each x value, we can express, instead of having to sort of go through and say, get the list of values for every point on this x-axis here, we can simply express the mean of this normal distribution and the variability of this normal distribution. So the mean, it probably would make sense to assume that the data came from a group, or the peak, I guess the mean again of this belief distribution is going to reflect where the peak of it is. So we probably have peak credibility, minimum surprise at a value of about 100. So we'd express our beliefs. Let me do it maybe, I don't want to overwrite. So, n of, say, 100. So it's going to be peaked at 100. Oh, so close. But what should we sort of put here for the parameter expressing how wide this distribution is? What is that conceptually doing? Well, let's imagine two scenarios. A scenario like this where this belief distribution is relatively wide versus an alternative scenario where I maybe have, I'll sort of dot it out, a belief distribution that peaks at the same point but has a much tighter shape. So they're both poorly drawn normal distributions centered on 100, but the darker curve is wider, and so it would have a larger value right here, and the dotted curve is narrower, so it would have a smaller value right here. What would you interpret as the difference between these two belief distributions? What are they saying differently?
More variability, like the wider the distribution, with more variability in your population. So it's more narrow.
Okay, remember this is about beliefs.
Our beliefs are more narrow.
Yeah, no, that's exactly it. Is that the narrow distribution reflects sort of a narrower set of values for whatever parameter we're dealing with down here that it can take. So you're not very surprised by 100, but you're fairly surprised by say like 110, and that so. Whereas this darker curve, you're not surprised by 100, you're not super surprised by 110, but it only gets out to when you get to like 140 or whatever, you start getting sort of really surprised by data. So the thing that goes here when you're talking about the distribution of beliefs really specifies how certain you are about that the value is close to this thing that you put here. So again, this specifies where your peak belief is, but it's going to taper off on either side, and the value you put here really specifies how certain you are. So if you're very certain, that's going to be a small number. If you're very uncertain, it's going to be a big number. So if we were to take, say, a distribution like this, if you were to have 20, so let's,
That second number, that's like the standard deviation, right?
yes, yeah, it's specifying the variability of this normal distribution that we're using to sort of draw the shape of our beliefs. But it will, yay, 20. So if I were to use a value of 20 there, that just specifies a certain width. And you can actually just, in R, if you want to explore like what the shapes of those distributions are, let me actually switch over to R. I will keep that up there, and I'll maybe just add some stuff at the top of this script. So put this way up. Okay, so I'm gonna show you guys how to just draw out the curves relating to these normal distributions. So we're gonna use the curve function. And the curve function, actually I should look it up. Help, curve. The first argument is called expr. And that's gonna be equal to something. I'm going to actually put in the other arguments too, from equals. This is asking sort of on the x-axis, what's the limits of the x-axis? So I'll say go from 60 to 140. All right, so what's in the expr is a curve is asking for another function to use to draw. So we're going to use the dnorm function. That actually plots the curve, the density, probability density curve of the normal distribution. So dnorm takes two arguments, x, which we'll just leave there. Curve will handle putting in x values and from 60 to 140 and evaluating dnorm with those x values. So we need to just leave x there like that, but dnorm as a normal distribution, it takes two other things. I think it's mean, or is it mu? Yep, mean. Mean equals, say, 100, and SD equals, say, 20. So this is just going to draw a nice little curve. And you can get a feel for like whether that accurately captures how surprised you'd be. So again, big values, not very surprised. Small values, fairly surprised. Let's actually make sure the y-axis goes all the way down to 0. So you can set that again in curve. Y_lim equals c. We'll put 0, and then 0.02, I guess, is the top there. Okay, so you can kind of get a feel for like the range that this curve takes on the y-axis, and therefore the sort of relative credibility that different values take. So this is actually pretty broad. Like you might be, there's still fairly non-zero probability way out to the group having a mean of 140. And again, we're talking about, when I say group, I mean the population from which my given sample might be drawn. So this is a pretty broad prior. If I wanted to express a more narrow prior, maybe I'll say SD of 5. And now it's gone past the limits here, so I have to just change what the limits are. So let's go 0.1. So here, the y-axis has changed, but the important part is the relative position, the relative heights of these things. So now 140 is pretty much 0 probability, so I'd be very surprised. Even 120 now is 0 probability, whereas values, say, around 110, moderately surprising, and values closer to 100 are still not very surprising.
You were kind of guessing the from and the to because of your previous knowledge, right?
Yeah,
But
yeah.
if I have no clue about mine, what should
Okay, we'll get into scenarios where you're much less certain about everything as we go. The short answer is that we'll be using the range of the data itself to help us decide what priors to do. In essence, you turn the data into z-scores, so you divide by their variability, and that helps you set then priors that establish the reasonable spread of belief. But for this particular example, in general, it probably makes sense to use what are called relatively weakly informed priors. Weakly informed just means a big spread. So a narrow spread like this, 5, that would be maybe considered strongly informed. Whereas if I had something like 20, that's another way to sort of compare those two priors is this looks way more spread than that earlier one. So this is what would be called a weakly informed prior. You can imagine sort of the extreme of this, which would be just a flat line, uniform. Now that would be a normal with an infinite standard deviation. You could alternatively just use, instead of a normal distribution, a uniform distribution from negative infinity to positive infinity. You generally don't want to do that because you can express at least some reasonable expectation on the data, and that will help things computationally. So we'll generally be using relatively weakly informed priors. Okay, so you can use this code to explore like what different choices for the prior actually look like. Let me go back to my drawing. So let's say we decide that 20 is sort of a reasonable value for expressing our prior beliefs. Now we have a scenario where, again, we have a generative model. So, well, we have data. We have a generative model for that data. That is, we think that these samples down here were drawn from a normal distribution with some mean and a definitely known variability of 15. And when we talk about that some mean, since we're uncertain about what it should be, we can express a prior for that mean. So we wouldn't be very surprised by or we'd be least surprised by a population with a mean of 100. But we have some variability in the degree to which we'd find various values here surprising. So we model that as a normal distribution that tapers off sort of with this gradual curve of 20 that is over in our window over here. So with all those pieces, we can now start doing Bayesian inference. So what we're actually going to get out of this is we're going into the data, we're going into the analysis with this prior, so centered on 100 with the variability of 20. This prior sort of expresses we're uncertain as to what population mean is generating the data. We then observe some data, and that's going to allow us to update the beliefs about what the population mean generating the data is. So after combining the data with the prior, we'll get a new distribution. Again, it's going to be on the scale of IQ. It's going to reflect what we should believe as a belief distribution now that we've updated our prior with the data. Now, our prior is centered on 100. The data have a mean that's a little bit off 100, so it's very likely that the prior is going to, or the posterior, this distribution that reflects what we should believe after we've integrated, we've updated our prior with the data. The posterior should shift a bit towards the mean of what the data have, but it won't shift all the way. The degree to which it shifts is influenced by the sort of amount of certainty we went into things. If you're very certain that the population's mean is 100, then the data aren't going to shift you very much, even if the data has a mean that's different from 100. Conversely, if you're really uncertain about the value of that population mean, you are going to shift fairly considerably towards the sample mean. And so that's the influence of expressing sort of how certain you are. That sounds like, wait, couldn't I get any result I want by working backwards from working or just trying different prior widths and deciding on one that sufficiently shifts my data? Well, for any prior specification, there's going to be sort of an amount of data that is able to shift it. And in general, we'll talk about methods to choose priors that will make it relatively objective, so people aren't going to accuse you of just choosing a prior that happened to get the result you wanted. But let's accept that you guys decide that this prior describes your beliefs. Well, normal of 120. We've got a generative model of some mean and a variability of 15, and we have this data observed. So what we're going to do now is shift to working in R. We're going to generate some data, and then we're going to look at the stand code to express both the generative model and our prior beliefs. And then we're going to jump back into R to, given that stand model, give it the fake data and ask what the posterior is going to be. So, any questions before we start? Yeah. Simply because in terms of talking about generative models, it's easier. There's not many generative models that have a parameter that is the median. You can do inference on the median, okay. I haven't thought about including that, but we can. Actually, no, that will be discussed in the context of what's called posterior predictive checks, but we're not going to talk about that for a couple weeks now. All right, so this first example that you can get by going to that GitHub site starts off with a little title, one group known error variance. So this is just a descriptor for this particular scenario where you have just one group, a sample of data from one group, and we're assuming we know what our generative model has a known error variance of the normal, so it's 15 in our case. That just explains that title. This little bit here probably isn't necessary. This is just a little snippet of code that will clear the workspace, our workspace or the environment. It actually doesn't have anything in it anyway, so running it doesn't matter. This next bit will load up RStan. If you've installed things correctly, let me shift this so that it's actually all fitting on screen. If you've installed things correctly, that's going to show some startup messages. We'll ignore these startup messages for now. Ditto, I'll load up ggmc. Ditto, some startup messages. We're going to ignore them for now. The next little bit is just so that we all get the same numbers. You actually don't need to set this now that I think about it. All this does, so R is going to generate random data. If we don't do this, we are each going to get different random data. If you run this piece of code, it will make sure that you always get the same random data every time. That seems like a contradiction of terms, the same random data. That's because with computers, you're never getting random data. At least with the way randomness is done in R, it's using pseudo-random data. So it uses an algorithm behind the scenes to generate random data, and you can what's called seed that algorithm with a number. And whenever you use the same seed at the outset, it means that you're going to get the same random data anytime and on any computer that you're running it on. All right, so set the seed, and if we do this bit, so it says generate some fake data, and it has 1E4 here. Let's not do that. Let's just do, say, 30. So our norm, well, actually, let's step through this code. Saying Y, so it's going to create this new thing called Y, capital Y. In it, we're going to put the result of a call to our norm. Our norm is the way to generate random normal data. So the first argument to our norm is, what's it called? Hover n. So that's the number of data points to sample. So we're imagining going out to, again, I think we were talking about PEI, finding 30 random people in PEI and getting their IQ. So that's what that 30 means. This little bit is saying grab random normal data with a mean of 100 and a standard deviation of 15. So for the purpose of generating this fake data, we are setting what the population's mean and standard deviation is. If we know what the population's mean and standard deviation, we now don't have to do any more inference. We're done. We already know it. We don't have to ask questions about what the population mean is. It's right there. It's 100. I'm going to ask you guys to forget that you saw this line. I want to ask you guys to run this line and then forget that it's there in the code. So imagine that you just have this thing Y that's, say, let's forget that we ran that code. What if you were to just have these data points? So 30 observations of IQs from people in PEI, and you wanted to know what would be sort of a reasonable set of beliefs for the population mean without looking at the actual code that specifies what the population mean is. Okay? So we want to know what sort of normal distribution generated Y. All right, that makes sense. We're generating some random data, but immediately forgetting how we generated that random data to put ourselves in the place of a real researcher that's gone out and done some data collection. All right, so now that we have some random data, we can then give it to, we need to eventually give it to Stan. Stan requires that you package it up in a nice little format. So we're going to create a new object that we'll arbitrarily call data. And in that object, we're going to put the result of a call to the list function. So the list function just puts things together in a common bucket that allows you to name items in that bucket. It's like a data frame, kind of, except a data frame requires you to have that nice rows and columns format where every column has the same number of rows. With a list, you can have named things, just like you can have named columns in a data frame, but with a list, each thing can be of its own size. So we're going to give it Y. So with a list, the thing on the left-hand side of the equal names the thing, and the thing on the right-hand side is the value that you're going to put in that thing. So down here at the second argument, we're giving it Y. We're saying create an object inside this list called Y, and inside of it, put the contents of this Y that we created. initially we're creating this thing called ny. That simply contains the value corresponding to how many items there are in y. That's what length y does. Is it goes in, it looks at the thing called y that we just generated and asks how many items are in that thing. So this list then, if we create it and we immediately say print data, and it's a bucket that has 2 items. The sort of item names are shown here in the printout as having a prefix of the $sign. That's to indicate to you that you can refer to that thing by name, saying data $ny or data $y. So the ny, the item called ny just has 1 element, 30. The item called y has 30 elements, and those are all the observations that we need to deal with. So that's how you want to package up your data for Stan. It needs to be put into a little list. Below here is going to be work to actually use Stan, but let's actually go look at the other file that's in that folder that has the .stan extension here. If you click it, it will actually open up its own little thing over here. I'm going to click this button here, which will grab this text window and give it its own big window. That way it's not competing with the console window for space. So I'm going to grab it, it pops it out, it's over on my other screen, so I'll pull it over here. So it's that same window. I'll make it big. One reason I do that, particularly when looking at Stan files, is because there's a sort of bug in its code such that it is set to wrap these comments. If I make this a smaller size, notice how the line suddenly sort of increases in size. It doesn't put a scroll bar at the bottom, it just like wraps the text around. I hate that. So I make a big window so it doesn't sort of have to wrap around. So this is our Stan code. Again, this is just a text file in the same way that all your .r files are text files and get fancy highlighting because you happen to be opening it in RStudio. If you open it in a text editor, it will open, but it'll just be black and white. Stan is the same. It'll just be black and white in a text editor, but RStudio actually knows about like things in the Stan language, so it's able to put nice colors on things. So just like in R, you can use a number sign to indicate that you're doing a comment. Unlike R, you can also do comments by // so you'll often see that in a lot of the formal Stan code. I think most of the time I'll just use a number sign. But there's a couple other sort of things to notice in this file. There's 3 main sections: a data section, a parameters section, and a model section. Each section starts with the name, so data, and then has squiggly brackets and some stuff inside the squiggly brackets. How am I doing for time here? Okay, great. So the data section is pretty straightforward. We can kind of infer that it has the same kind of structure as what we had for code in packaging the data up for Stan. So this section tells Stan what to expect in terms of data coming in. So there's 2 lines. So there's 2 things that we're telling Stan to expect to receive. Another general thing to notice about all these all the sections is that every line ends in this little, well, every line has its own comment. That's beside the point. The big thing is that every line ends in a semicolon. This is because Stan, well, anytime you're sort of finished doing something in Stan, you need to have this semicolon. So this line serves to tell Stan to expect something called ny, and then we're done telling it what to expect. this line says, okay, expect something else called y, but we're done telling it about what to expect next. So that's just something that you have to remember, is to always put a semicolon at the end. I really wish they could take that out, but it's actually common to a lot of languages. R is a little bit different, that you've had the convenience of not having to remember to put that in. That's going to be one of the big things that you forget. So in R, you probably have encountered, oh, I forgot to put an extra parenthesis, or I forgot to put a comma somewhere. Here you have to remember about those, plus remembering to put a semicolon at the end of each line. Notice that the lines that kind of delimit the sections don't have those semicolons. That's because sort of they don't need it. So the lines inside a section need the semicolon at the end, but the lines outside the section don't. All right, so again, talking about this data section, in our R code, we created a list object that had two things in it. And in this section, we've got sort of two lines, but they've got a whole lot of extra stuff on them. So it says int and then ny. What is this int bit? Well, that's telling Stan to expect an item called ny, but it's a single thing. It's a single value. And more specifically, it's a number that can only be like 1, 2, it's an integer number. So it shouldn't expect decimal places or negative numbers there. We know our data object has a value 30 there. But if we want to reuse this code for other things with other lengths, we can make it flexible to accept any number for the length of the data set, but we know that if that's going to specify the length of the data set, it's always going to be an integer. It's never going to be a negative number or a decimal. Why do we have to give it, even tell it how much data there is? Presumably we're giving it the data, so it should be able to count how much data there is in the first place. Well, that's because when we tell it that we're going to give it something called y, we have to tell it it's a list of things. It's a vector. Remember, in a lot of computing languages, vector merely means a list of numbers, and all the items are the same, i.e. they're a number. We have to tell it what we have to. It will automatically use this ny variable to set the length of that vector. So it's not smart enough to see that there's something called y and automatically infer what length that set is, that collection of numbers. You have to tell it, I'm going to give you a number here and use that number to set the length of the how much data you should expect in this object called y. So you have to do a little bit more work to sort of define variables or set up variables in Stan. You have to think about what potential values, is it a list of values and how many are there, and what are the potential values that I might need to put in there? Is it just integers, or is it sort of any value? Any questions about that so far? This section here dictates what you will do in your R section to package up the data. So you may have been confused why I was giving it this thing called ny. Why couldn't I just give it y as the only thing in this list, in this bucket? This is why, is because the just because of Stan's quirks, it needs a thing telling it how long any vector is going to be. Any questions about that so far? All right. So the rest of this code is about specifying the generative model and our beliefs about unknown quantities in that generative model. So let's skip down to the model section here, where it says y tilde normal mu comma 15. Well, that seems really familiar to our plot here, where I've got this section here, and I told you that this is our generative model. All right, so instead of just the n, you actually have to write out the full normal, and instead of x, I decided to call this thing mu, that reflects the population mean from which the data are sampled. But otherwise, it's the same. And of course, we've got this little semicolon at the end. So this is our generative model part. Now I've got this thing called mu, expressing sort of a parameter we're uncertain about. So if that's any parameter that's uncertain, you have to initialize in the parameters section. What I mean by initialize is that you're telling Stan what values it can take. So it's not an int. The IQ doesn't have to be 101 or 102, 103. It could be 101.5. It could be 98.6. It could even be a negative number, even though that's actually not real in the world of IQs. But we'll pretend that we're not going to care about the fact that IQs can't be negative. So when you have something that isn't an int, but can take any decimal value or even negative values, you initialize it by saying real space and then the name of it, so mu. So this bit tells Stan that it should expect a parameter that we're interested in doing inference on, and that parameter can take any value on the number line. So again, this is our generative model. This is sort of set Stan up to what sort of possible values the parameter in here, this unknown parameter in here, can take. What's the one last thing that we need to talk about in terms of a Bayesian model? Well, it's the prior. So we've told it that there's some unknown thing. It can take any value, but what do we believe about the possible values that this could take at the outset, having not seen data yet? So the prior specification looks kind of like the specification for the sort of generative model part. You have mu, tilde, normal, and then a couple of numbers here. And this should look like what we had for the specification of a prior that we had up here. So we said that we will believe most in a value of 100, so it should be a normal centered on 100. Normal centered on 100. And we decided that the shape that a normal 120 forms seems relatively reasonable as a sort of weakly informed prior for what mu is. So there we go. We've specified the data coming in, what its structure is going to be. We've specified that there's a generative model that is going to have a parameter called mu. We've specified our sort of prior beliefs for mu. And we've specified the explicit generative model that uses mu and talks about how this unknown parameter plus this other known thing combine with the normal distribution to specify how we think y was generated. Is that any questions on the general structure of the Stan file and how it sort of includes all the things we've been talking about so far, that you've got data, a generative model, and a prior for any sort of unknowns in that generative model? Yes, 10 minutes. Okay. So with this .stan file, which I'll actually save just in case, we can now get ready to, and with our data, so we've got data in R, we stored it in this object called data, we can get ready to combine the two. So the model, that model file could be used on any data set, and we want to apply it to the data set that we're actually dealing with here. So this next little bit, you can actually probably delete a bunch of it. So the lines from if all the way to else you can delete, and the last two lines from save to the last squiggly bracket you can delete, so that you just have that line model. So what this is doing, let me actually expand it. We're creating an object called model, and in it we're putting the result of this bit over here. So what is this bit over here? We're saying look in the rstand package and find the function called stand model. You actually, since we put library rstand at the very top, we actually don't need this little bit there. I just happened to be feeling verbose at the time, so I want to be explicit that the function stand model comes from the package rstand, and that's what that 2 colons means if you ever see it. So it's calling the stand model function, and that function has, we don't know what it does yet, but it has a single argument called file. And that argument we're passing as its value this string that simply is the file name of the file that has the model we're interested in. So what that's going to do, what does this stand model do? It looks and it gets the file that we refer to, and it compiles it. We haven't talked about compilation at all because so far we've only been dealing with R, and R is a non-compiled programming environment. Whenever you want to do a computation, you just do it. 1 + 1, enter, and it does it. A lot of other programming languages, particularly those that are older, C, C++, etc., you have to write the code and then turn it into something that your computer can understand, and then do the computation, then use the code. It's an extra step that you don't actually need to worry about what it's doing behind the scenes, except to know that sometimes when you compile your model, you'll get some errors, and those errors will tell you about things that sort of are awry with your model. So if you forget to put a semicolon on one of your lines when you go to compile the model. In fact, let me do that. I'll forget to put a semicolon, and then I'll go back to RStudio, and I'll run this little section that tries to compile the model, and I'll get a syntax error message from parser, and it says error at line 8. It shows me sort of where some of the lines leading up to line 8, and it says expected semicolon. So it kind of gives me a hint that it said expected a semicolon by line 8. So if I look at line 7, I can see line 7 was missing its semicolon. So I save and go back, and if I rerun this line, it will go without any immediate error message. It's still not done yet. It's still it's like taking time. If I bring up my activity monitor, you can see the CPU load. It's actually doing something. And the highest CPU user is Clang, whatever that is. That's compiling this little piece of code into something that the computer can use to run the model. It means that the model actually runs very quickly once it's done, but it's just, again, an extra step you have to do when dealing with stand versus other things that you do typically in R. So now that we've compiled the model, we can use it. We can start combining the model with our data to ask about what we should believe now. This little bit, again, I want to simplify for what we're doing now. So, well, no, I will actually walk through this. Again, okay, 2 minutes. Okay, quick preview. You can ignore all this, what's going on. I'll walk through it in more depth when we return on Friday. We run this command from the RStan library called sampling. We give it the model that we just compiled. We give it the data, and we set a couple other things. Critical is that the sampling function takes the model and the data and spits something out. What is that thing that it spits out? Well, it spits out sort of a representation of the posterior. Again, we had a prior on what we might believe about the population mean going into the experiment. We sampled some data. We combine the Bayesian methods allow us to combine that data with the our prior information to update our beliefs, yielding a posterior distribution for our beliefs. So mu is that parameter that we're talking about. We had that data y that had that. If we look at mean of y, the mean of y was about 95. We went into the, in our model code there, we expressed a belief centered on 100, but very broad. What this bit means, again, just a quick preview, we'll walk through this more slowly next time, is that the mean of the distribution being spit out from the analysis is centered much closer to the mean of the sample than it is to our prior mean. So our mean belief has shifted. And the other two sort of critical things you get out of this is sort of the spread of our beliefs. So you can ask about sort of where is the bulk of belief after we've updated from the data. And most of our belief falls between 90 and 101. So we're pretty sure, like we would believe values between 90 and 101 as the true value now that we've seen this data. We wouldn't believe a value for this population of, say, 120, given the data that we just observed. But we would be fairly credible of a value of, say, 93, or certainly 95 is sort of our new peak belief for this data. A visual representation of this distribution can be seen from running the next little bit. We can get a histogram of, again, our beliefs. Oops, so here's a nice little histogram of sort of, again, this is the posterior distribution on our beliefs. Why is it a histogram? We'll talk about that later versus a nice smooth curve. We'll talk about that next day. But yeah, kind of ran out of time, so I had to rush the last little bit, but we'll go back over this last little bit next time.
How do you open a separate scan file?
A what, sorry?
How do you make a scan file to put model into?
Well, I usually just copy an R file, so I copy, and you can rename it.
I tried to save as, and it made it .scan.r.
Ah,
That's like just a normal?
yeah,
Okay.
yeah.
As long as I'm not doing something